And we are and then on Friday, we're going to move on to fluids and states of matter and good stuff like that. So we're going to take a slingshot. And at the end of my slingshot, I've got a mass. We're going to say that we're doing 10 revolutions per second. Our radius is going to be 0.5 meters. The mass of our little ball or rock or whatever you want to say it is going to be 0.25 kilograms. We want to find our angular velocity, our moment of inertia, and the kinetic energy. So this is my David and Goliath problem. So we're actually given an angular velocity. We're given it as 10 revolutions per second, but we know that we want to actually convert that to radians per second. And there's 2 pi radians to 1 revolution. So we're going to end up with 20 pi radians per second. And if you want to calculate that out, that's going to be 62.8 radians per second. Now, my moment of inertia for this system is going to be my I is equal to mr squared. We have our mass is 0.25 kilograms, and our radius is 0.5 meters squared. And that's going to give me 0.0625 kilograms meters squared. Now, this is where things get really interesting. So my moment of inertia is kind of small. This is actually kind of a slow slingshot, but look at the kinetic energy. The kinetic energy of this is going to be 1/2. I'm so used to writing it the other way, 1/2 I omega squared for something that's in rotation. And this is going to be 1/2 0.0625, and I've got kilograms meters squared. My omega is 62.8, and that's 1/seconds squared. And this is going to end up being 123 Newton meters, which is 123 joules. That's an awful lot of energy that we are imparting to the mass. So if this is a David and Goliath situation, we could look at the total energy of the mass as it leaves the slingshot. So the total energy is going to equal the kinetic energy of rotation plus the potential energy, how tall above the ground we are. And we're going to assume that our person is 2 meters tall, about 6 feet. Okay. And we're going to get 123 joules plus my 0.25, 9.81, and I'm going to be at 2 meters. So I've got that part in there. And so I'm going to end up being 128.6 joules. So that's going to be the total energy of the slingshot as it leaves that person. So let's see, how far will it travel? So now we've got my person here, and we've got the rock, and it's going to actually go off in a distance, and we know it's going to be a projectile motion. We want to know how far it's going to travel. So we know our change in height because we said it was going to be 2 meters. Because we said this was going to be 2 meters up. And so our velocity in the y direction times time minus 1/2 gt squared is going to equal my change in y. This will give me time of flight. So we can figure that out. My initial velocity in the y direction is 0. So we're going to get a minus 1/2 gt squared is equal to a minus 2. T squared is going to equal to 4g. Or no, it's going to equal to 4 divided by g. T is going to be the square root of 4 divided by g. And I'm going to get 0.638 seconds. Now, my velocity in the x direction is going to be r omega. So we're going to get our 0.5. We already calculated omega as 62.8 radians per second. And that's going to end up being 31.4 meters per second. So look at that number. So we're actually going to be over 60 miles an hour for that ball, that rock to be coming off of the slingshot. So now we can calculate distance. Distance is just VXT. And we're going to get 31.4 meters per second times our 0.638 seconds. And it's going to go 20 meters. So a slingshot is a pretty good tool. Slingshot is an excellent tool. So I kind of walk through those problems, and that kind of gets us back to where we were on Friday, because Friday we were starting with our moment of inertia, or our angular momentum. And remember, my angular momentum is going to be I omega, where this is going to be my angular momentum. And we were kind of warming up to the fact that we all know that if I have a figure skater, and my figure skater has a narrow radius, that this person is going to be spinning faster than this person. If I'm extending out, I have my leg out and my arms out, and this radius is bigger than this one, and this one's going to have a slower spin. And you guys have, I would encourage you to look at my videos that I have. There's a really good National Science Foundation Winter Olympics where they actually are showing the spin and the moment of inertia that's in this piece. So if we're going to do this, we want to look at that comparison of spin. We can actually look at that person. So we're going to start with a person that is, this radius for this person is going to be 0.5 meter. The person's got a mass of 50 kilograms. And we're going to calculate the moment of inertia. And our moment of inertia is going to be mass times r squared. So we're going to get our 50 kilograms times our 0.5 squared, meters squared. If I do that, I'm going to get 12 12.5 kilograms meters squared. This one, we're gonna have the radius. We're gonna give the radius to be 1 meter. Actually, we're gonna do 1.25 meters. Mass hasn't changed. So now I'm gonna calculate the moment of inertia. And this is going to be 78.125 kilograms meters squared. Now, this is the same one, so we're going to have the angular momentum before has to equal the angular momentum after. So we're going to have I initial, omega initial is going to equal I final, omega final. And we're wanting to know the new speed here. We're going to start out with this one being, let's make this 15 revolutions per second. So if I do that, I get my 15 revolutions per second, and it's 2 pi revolutions for one, or 2 pi radians for one revolution. So I'm going to get 30 pi. So I'm going to get I initial divided by I final, omega initial is going to equal my new omega final, which this is going to be, my initial one was 12.5. My final one is 78.125. And now I'm at 30 pi. Gives me 4.8 pi. And if we want to know the new revolutions per second, this is going to be 2.4 revolutions per second. So we go from 15 revolutions when we're in our tight spin to 2.4 revolutions in our slower spin, just because we have a lot of, or we've changed the radius. And we see that. I mean, if you've ever spun around on something, we see that. Okay, let's play with a merry-go-round. Or if you think about it, it could be a merry-go-round. So we're going to have a big disc. And the merry-go-round is a disc, and it's going to have, and we're going to tell you its moment, or its moment of inertia is going to be 800 kilograms meters squared. So we're going to be rotating this at 1 revolution per second. So that's going to be 2 pi radians per second. That's going to be our initial rotation. And this is why we call it a merry-go-round. So now I have a little kid. And let's say my little kid is sitting at a radius of 1 meter. And the mass of this little kid is 25 kilograms. And we've got the big kid that's sitting right out here at the end. And our big kid has a mass of 50 kilograms, and we are 2.5 meters away. And the big kid is going to jump off eventually. All right? The big kid is going to jump off. So we want to know our moment of inertia to start. Our moment of inertia to start is going to be the moment of inertia of the disc plus the moment of inertia of kid 1 plus the moment of inertia of kid 2. This is going to be the one that we've been given. This is going to be the mass of the kiddo, its distance away. And this is 1. And it's going to be the mass of the kiddo, its distance away, 2. So I got my 800. I got 2.5. This is all going to be in kilograms meters squared. So I got 25, and now I got to figure out the other one. 2.5 squared times 50 is 312.5. So now I'm going to have 1,037.5 kilograms meters squared. Now, the moment of inertia after this kiddo falls off or comes off, so that's going to be our final moment of inertia. It's going to be my 800 plus my 25, because we already calculated that. So I get 825 kilograms meters squared. So my angular momentum before has to equal the angular momentum after. And so I get I to start. My starting angular velocity is going to equal my I final and my final angular velocity. And so now we can calculate that. And this was 1,337.5. We're going to divide it by 825, and it was 2 pi radians per second. So now, after the kiddo jumps off, we're going to be doing 2.75 radians or pi radians per second. So it's definitely going to move much faster after this kiddo comes off. So we end up doing that. Now, if you want to know for a disc, just so that you've got that down, because discs are one that we use a lot, that's 1/2 mr squared. That's the equation for a disc. You can look these up in tables. And those are the 2 classic type problems that we do for rotational motion that we look at. So we are done with chapter 8. We're done with it. Questions?